Before the lecture starts, please be reminded that you're to turn off your mobile phones, pagers, or any beeping devices into silent mode. Thank you for your cooperation. Good morning, ladies and gentlemen. Welcome you all to the Saul Prize Lecture in Mathematical Science, where we celebrate and pay tribute to the pinnacle of academia through a tradition that rewards pioneers with not only vision, but intelligence and persistence. My name is Raymond Hong, a third-year student in the Actuarial Science program from the Faculty of Science. Today, it is our great honor to have both Saul laureates in mathematics, Professor Clifford H. Taubes and Professor Simon K. Donaldson. The Saul Prize is established in 2002 by Sir Run Saul, a leader in the media industry in Hong Kong, and a longtime philanthropist, to honor individuals regardless of race, nationality, and religious belief, who have achieved significant breakthrough in academic and scientific research or application, and whose work has resulted in a positive and profound impact on mankind. This morning, we're so honored to have two of the outstanding laureates who have made great contributions to the world of mathematics, Professor Clifford H. Taubes and Professor Simon K. Donaldson. They are the co-winner of this year's Saul Prize in mathematics for their many brilliant work in geometry in 3 and 4 dimensions. We're so delighted to have all of you here today at this meaningful event that focuses on this field. May I now invite Professor Richard Wong, the acting Vice Chancellor of the University of Hong Kong, to give a welcoming address. Professor Wong, please.
Professor Donaldson, Professor Taubes, Professor Yang, distinguished guests, colleagues, students, ladies and gentlemen. On behalf of the University of Hong Kong, I would like to extend a very warm welcome to all of you. It is indeed a privilege for the university to host the Saul Prize Lecture in Mathematical Sciences this year. And I'm delighted to welcome the two distinguished Saul Prize laureates to Hong Kong U. The Saul Prize was established with the generous support of Sir Run Saul, whom we are proud to call an honorary graduate of this university. And indeed, we are in a building that he contributed much to. It is very much an honor that two such distinguished scientists will be sharing their insights, expertise, and experience with us. Our Saul Prize laureates, Professor Simon Donaldson and Clifford Taubes, are two geometers who have transformed the whole subject of three-dimensional space and four-dimensional space-time by pioneering techniques and ideas originating in theoretical physics, including quantum theory. Between them, Professor Donaldson and Taubes have totally transformed our geometrical understanding of space and time. This idea of making transformational discoveries may be especially potent during the times of great change that we live in today, for they represent not only an enormous contribution to knowledge, but also give rise to an encouraging sense of positive empowerment, when so many developments in our world often seem to be out of our own control. This idea of empowerment through teaching, learning, and research has also been an important philosophy here at the university. Indeed, is a key part of its raison d'etre. The university was founded in 1911 to provide a modern tertiary education for local students for the benefit of Hong Kong and China. But throughout its history, and particularly before the Second World War, we attracted students well beyond our local shores. And since the past 20 years, we are back attracting students beyond our local community. Almost a century on, the university is moving with the changes that have affected our world, building on the strength of its own history and finding new approaches in university education to meet the needs of an internationalized, knowledge-based economy. In doing so, Hong Kong U has developed a reputation for academic and research excellence that is recognized. We will continue to move forward with this dedication to excellence and to extend our mission of service across the global community. And it is in this spirit we really welcome not only the establishment of the Shaw Prize and the good work it has done, and we're particularly proud that we are able to have this opportunity to hold this particular occasion. And my congratulations to all those who have worked so hard to make this an important and memorable occasion. Please join me in welcoming Professor Donaldson and Professor Taubes.
Thank you, Professor Wong, for the warm address. And please stay for the souvenir presentation to our guests. May I now invite Professor Taubes to ascend to the stage.
Thank you so much. Thank you.
Thank you, Professor Taubes.
I stay here. Okay.
May I invite Professor Donaldson to come forward to the stage.
I'm looking forward to it very much. Thank you very much.
Thank you, Professor Donaldson and Professor Wong. And in this memorable moment, let's take a group photo together. May I now invite Sir Michael Attier, the chairman of Selection Committee, the Shaw Prize in Mathematical Science for 2009. And Professor Yan Chen Ning, the chairman of Board of Adjudicators of the Shaw Prize 2009. And may I now also invite Professor Kwok, Professor Sun Kwok, the Dean of Science. Thank you, and may all the guests please resume your seats. Now may I invite Professor Sun Kwok to introduce the first speaker. Professor Clifford H. Taubes, the Shaw Laureate in Mathematics 2009. Professor Kwok, please.
Acting Vice Chancellor, honorable guests, ladies and gentlemen, the Faculty of Science is indeed very much honored to be the host of the Shaw Prize Lecture for Mathematical Sciences in 2009. And the prize this year, as we have heard, awarded to Professor Taubes and Professor Donaldson. I am an astronomer myself. I can't claim that I understand much about their work, but I did do a little bit of reading, and it seems to me, as I understand, the origin of the work can be traced back to the 19th century, when the geometry of two-dimensional surfaces developed into the theory of Riemann surfaces, and in the early 20th century, when Poincare introduced topological ideas into this problem. Our two speakers today contributed to the understanding of the topology of higher dimensions, namely 3 and 4, which turned out to be much more difficult than the perhaps similar associated problems at 5th or 6th dimensions. And our first speaker, we have 2 talks today. The first talk is titled Loops, Surfaces, and the Structure of 3 and 4 Dimensional Spaces, given by Professor Clifford Taubes. And Professor Taubes is currently the William Patrick Professor of Mathematics at Harvard University. He was an undergraduate at Cornell University and received his PhD in physics from Harvard University in 1980. He received many awards, among which the AMS Veblen Prize in 1991, the Eddie Carden Prize in 1993, Clay Research Award in 2008, and the NAS Award in Mathematics in 2008. He's a member of the National Academy of Sciences of the United States of America. Professor Taubes. Oh, I'm sorry.
Thank you. Well, I want to thank, first of all, the good people at Hong Kong University for allowing me to lecture here, and of course the Shaw people once again for their honoring me and for treating me so well here. I've truly enjoyed my visit to Hong Kong. This is my 2nd time here, and I enjoyed my first visit very much, and I'm certainly enjoying this one. Okay, so what I thought I'd do is I would give a lecture sort of introducing, to some extent, the sorts of questions that I and Professor Donaldson and others have been thinking about, and so I hope to give you some idea of, really what we're trying to do. And so that's sort of my goal in the lecture, and I guess you guys will decide whether I succeed or not. So the central issue is, the shapes, what is the shape of space? So, the basic point to think about is if you start with a space and, think about the surface of the Earth, for example. If you're on the surface of the Earth, well, there's sort of hills and local topography, but basically it looks pretty flat, the surface of the Earth. But of course the question is, what does it look? So on a small scale, we're talking about spaces that, are pretty boring. They all look the same. And then the question is, what does it look like on the large scale? And this question, of course, was a fundamental issue to the ancients because, because the Earth looks pretty flat on small scales, there was a widespread belief that the Earth, in fact, was flat on large scales. And I don't know a lot of ancient history, but I do know the Greeks knew otherwise, and the Greeks, in fact, knew the Earth was round. And so in fact, they had 3 lines of evidence for this. One was you could see the shadow of the Earth when the moon was eclipsed, and from their knowledge of geometry, they knew the Earth was blocking the sunlight, and so they could see the round shadow on the moon. They had other evidence, which is if you put a stick vertically into the ground and look at it at noon on the same day, say in Alexandria in Egypt, and in Athens, the angles will be different. The length of the shadow, if the stick is the same size. And they actually had a third piece of evidence, which I found absolutely brilliant. And the third piece of evidence was that if you went west, well, southwest, but anyway, if you went west from Greece, you would find elephants, African elephants. And if you went east from Greece towards India, you would find elephants. And so they made the obvious conclusion that if you go west, you'll get east, because there are elephants in both directions. And in fact, this is stated. There's a recently published book, annotated text of a Greek mathematician, astronomer named Gemino. It's called Gemino's Introduction to the Phenomena, and he actually makes this case. And actually what he does, in fact, the Greeks were totally brilliant. Postulating the Earth was round, they actually concluded that there must exist a southern hemisphere, an antipodes to Greece, and that it would most likely be inhabited by people, but because of the equatorial region was too hot to cross, namely the Sahara Desert, which they knew about, they had no contact with this hypothetical southern race, but they postulated the existence of a southern hemisphere and people living in it. Okay, so we know the Earth is round, and as you know, my interest is in the surface of the Earth is something we call two-dimensional, and my interest is in 4 dimensions. So let me digress for a second and say a little bit what I mean by dimensions. So the dimensions of a space. So space can be any, in principle, any number, any positive or non-zero dimension. So the dimension is the number of coordinates, namely the coordinate being just a number. You need to specify to exactly, precisely say where a given point is. So for example, if we think of a one-dimensional space, dimension 1, well, what's an example? The example of a one-dimensional space is, say, the rim of an analog clock. So you see that clock up there? So I can tell you that where the big hand is without, by giving you just one number. I say the big hand is at 1053, and you know exactly where the big hand is. So the rim of the clock is something we call one-dimensional, because you only need one number. On the other hand, if we think about two-dimensional, then the surface of the Earth, and I'm thinking now the surface, so think of the surface of a globe. The surface of the Earth is two-dimensional because if I want to give you tell you where someplace is on the surface of the Earth, I have to give you its longitude and its latitude. So, for example, if I wanted to say, somebody wanted to go to my lecture, and I had to say where it was, I'd say, well, the Racine Wang Theater, it's 22 degrees, 16 minutes, 56.81 seconds north latitude. And it's 114 degrees, 8 minutes, 19.30 seconds east longitude. And those coordinates will get you within probably 20 feet of the building if Google Maps is accurate. Okay, so here we are, the Racine Wang Theater. We found it. But that's not enough. Okay, so the surface of the Earth is three-dimensional. Two-dimensional, but what about three? Well, if we think about the surface of the Earth, but a solid, and include, going up into the atmosphere, so what we think about space, then we have to give a third dimension. I not only have to tell you the longitude and latitude of the building, but I have to tell you what floor the theater's on, right? I have to tell you vertical. So, we could think of it as height above sea level. So it wasn't possible to get, using Google Earth, the actual image of this theater, but the ground floor of this building is 112 meters above sea level, okay? So I told you 112 meters above sea level, and if I tell you and go to the second floor, then you'll get here. So that's three dimensions. So you need three coordinates. We did three. And what about four? Well, okay, so you want to get to my lecture. So the real universe is four-dimensional. You want to get to my lecture. I tell you what time the lecture is, don't I? I have to say, well, it's at 10:50 on October 9th, 2009, local time. And then you'll be able to get to my lecture. Okay, so I have to give you four coordinates to make my lecture. And so we live in a universe which is four-dimensional. It's 4D. I don't know if you guys can see this. So we say 4 dimensions, 4D. Okay, so what I'm interested in is this, the structure of 4-dimensional spaces. Now, the actual structure of what the actual large-scale shape of the universe is something that astronomers and cosmologists, with their great instruments, and most likely, are discovering. So the actual shape of this particular universe is a question for astronomers. What I'm interested in is, in some sense, a list of all possible shapes the universe could be. A 4-dimensional space could be. So that's a mathematical question. That's no longer an astronomical question. So we're interested in, what are all possible 4-dimensional spaces? All possible 4D spaces. Okay. So what do I mean by that? What do I mean by a list? Well, all right, so let's start with 0 dimensions. So 0 dimensions, so I'll think of spaces that are connected, because you can always sort of take disjoints. So what's a 0-dimensional space? Well, there's only one of them, it's a point. So if you live at a point, you don't have to give any numbers. There's just one place to be. Everybody's going to be there. It's going to be crowded, but at least you don't have to worry about remembering your address when you go home. Okay, in 1 dimension, well, there's 2 basic 1-dimensional. There's a circle, which differ and then there's a line. So the line and the circle differ in that the line is unbounded in both directions. A circle, you go and you come back around to the circle being the rim of the clock. So the circle, the spaces that are bounded, what we call these are called compact. And I will just talk about compact spaces, because once you get into non-compact things, it's a little more complicated, and you might as well start with the simpler ones first, because we don't even understand the compact ones. Okay, so those are the only 2, turns out. So there's just a list of 2, and so right away you get optimistic because you think, well, that's easy. Dimension 0, there was just 1. Dimension 1, there was just 2. So what about dimension 2? Well, the list in dimension 2, the list is also known in dimension 2. And in dimension 2, well, what do we have? We have the surface of the sphere, which we know about because we can go up, the Earth is a sphere. But then there are others that, again, they all look sort of locally small scale, but there's another one which is basically the surface of a donut. So I don't know if they have donuts in Hong Kong, but so it's different than the sphere. It's still 2-dimensional because you can give two different coordinates, going around this way. But then there's a whole series of things. There's a surface that has 2 holes in it, which is kind of a pretzel. And then there's a surface with 3 holes in it, which is a kind of a 3-hole pretzel. And basically what you have is the apple, donut, 2-hole pretzel, 3-hole pretzel, and 4-hole pretzel, and then just a number of holes. And actually there's a second similar sequence which are called non-orientable surfaces, which are hard to draw because they can't be pictured in 3-dimensional space without having them kind of cross each other. So there's actually two sequences, not just one. But anyway, there's a whole list, and there you go. So 2 dimensions is understood, and this is understood since, for a long time, 1800s, I guess. Now, 3 dimensions, interestingly enough, was just recently, this was a very celebrated theorem of a mathematician named Grigory Perelman, who just proved what had been a long conjectured list. The conjecture went by the name of the geometrization conjecture by William Thurston, and it was just proved by Grigory Perelman about 3 years ago, a fantastic piece of mathematics. So we now know essentially what all 3-dimensional manifolds are. But let me give you an indication of what the list is. So there's a three-dimensional, so that what Perelman said and what the geometrization conjectured is there was a sort of a canonical way to cut up any given three-dimensional space into pieces. So there's canonical cuts, finite number of cuts, and each piece is one of 8 different building blocks. So you can make all three-dimensional spaces from 8 fundamental building blocks. And the analog here is if you think about what's going on in this two-dimensional example, if you have, for example, a 2-hole pretzel, if you cut it along this circle, you end up with these 2 building blocks that are just glued together along their boundary. And that's a kind of a very fundamental kind of construction, is gluing 2 things along a common boundary. And then if you take the 3-hole pretzel and you cut it along 2 circles, well, you get these two building blocks again, and then you get a 3rd building block, which is the one in the middle. And basically 4-hole and 5-hole are all, it's just basically these 2 different kinds of building blocks. You can build everything up. So, and in 3 dimensions, that's the same kind of story. You have some fundamental building blocks, and you can build everything from it. And so let me give you some examples. There's a 3-dimensional version of the sphere, and just as is in the 2-dimensional version of the sphere, you can think of it as taking two kind of disc-like things that have you curled up and sticking them together on the boundary. The 3-dimensional version of the sphere says take two solid balls, and now you'll see if you take 2 solid balls, you have the 2 different balls. Their boundaries are more or less the same thing. They're both surfaces of spheres. So you can identify you glue them along their boundary, and you get a 3-dimensional space. And what it means is this. It means if you started in this region and you started walking and you hit the boundary, well, when you hit the boundary, what happens is, of course, you go into this region because you've glued them along the boundary. So going from this region, you hit the boundary, and then because this boundary is glued here, you enter that region. And then if you wander in this region and go back out, you hit the boundary here, well, then you just come back in along here. And so now you have this closed space. And so one way to picture 3-dimensional spaces is by cutting them up. So these 2 balls together, glued on their boundary, is a space we call S3, S being sphere, and 3 being 3-dimensional. And here's another example, which is a space we call S2 cross S1, so 2-dimensional sphere cross. So think of a solid, let me start again. Think of a solid ball with a boundary which is 2-dimensional, and then take out from inside it a little inner ball. So there's 2 boundaries, the outer boundary and the inner boundary. And now you have 2 boundaries that are both spheres, so you can imagine gluing them together. Of course, you can't glue it together without sort of stretching it into, but abstractly think of it gluing together. So what happens is if you start inside and you walk and you hit the inner boundary, well, the inner boundary is glued to the outer boundary, so what happens is you come back in this way. You never leave it. You hit the inner boundary and then you come back in again. Or if you go out from here and hit the outer boundary, you might think you were leaving, but that's just a mirage. You're actually trapped and you come back in here and you're like, whoa, wait a minute, I can't get out of this place because it doesn't have any boundary because I've glued the boundaries together. Okay? And so, again, the way to think about 3 dimensions is you cut them up into fundamental pieces, and then you glue the pieces together. And what Perelman proved is that there's just the conjecture, and long-standing conjecture, which he proved there's just 8 fundamental pieces. Every 3-dimensional space, every possible can be obtained by gluing these 8 things together in various ways. Okay, so that's roughly the three-dimensional story. So what about the four-dimensional story? This is the interesting thing. Let me skip four dimensions, go to five-dimensional story. In five and higher dimensions, there's essentially a list. I mean, you have to be a little careful about what you mean by a list, but essentially it's completely understood. And this is due to work in the 60s, and to my great surprise, the person who sort of led all this is Stephen Smale, who's actually right here in the second row. So Stephen, maybe you want to stand up and introduce yourself. But there are other names. I mean, there are other, so anyway, there's a great deal of really beautiful work that was done in the 60s that understood five and higher. And so what about four? And in four, we don't even have a conjectured list. There's absolutely nobody has a reasonable list. I once made a conjectured list. I thought, well, conjectures, I can become famous. I'm never going to win a famous math prize, so second best thing is to have a conjecture named after yourself. So I stated in a lecture, well, here's a conjectured list, and some very smart guy came up after the lecture and said, Professor Taubes, isn't this a counterexample? So that was the last time I've made a conjecture. So I figured if you're going to make a conjecture, you better make a good one, at least. Anyway, nobody, as far as I know, has a conjectured list. But before we even start, so I'm talking about four-dimensional spaces. I gave you a way to visualize three-dimensional spaces. You can think of them as regions in our normal three-dimensional space. So, for example, a three-dimensional version of the torus, you can think of as a box. But the sides are identified. Opposite sides you glue together. So the opposite sides are all squares. So you can glue together the opposite. So think of it as a solid box where you've glued together the opposite sides. And so somebody who starts inside, well, the person starting inside thinks he's going out this way, but then he comes in that way. Or if he tries to go out the top, then he comes in the bottom. And so that's called a three-dimensional torus. We write it as T for torus, 3 for T3. So they're easy to think about three-dimensional spaces, but what about four-dimensional? So most of the time, you're not used to thinking about four dimensions. So as it turns out, magicians exploit four dimensions all the time. Okay. Now, I'm not a magician. I'm not even an amateur magician, but I did learn at least one magic trick, which does involve traveling in the fourth dimension. So the way this works, I need a volunteer. Somebody who wants to, please, step up. Step up, my young man. Youngster. So here's how this works. So you pick a card, you see, any card, and now you show it to the people in the audience, and then you put it on top. All right, now you may take a seat. Thank you. And now what happens, so the card is on the top, right? So I bury it in the deck, and then I sort of, doodle with the deck a while, and hopefully it doesn't come back on top. And then I get to pick out the card. I'm going to pick the card out for you guys. Now, how did this actually going to work? So I'm going to tell you how the trick worked. You weren't paying attention because you're all looking at him, but how this works is myself in the future, my future self knew I was going to do this trick. So my future self came back in time and appeared in the back of the room while you all were looking at the card, and my future self in the back of the room could see the card, right? So the guy, me in the back, so I was in the room twice the same person. My future self was in the room, and I'm in the room. Future self sees the card. Then the future self went about 20 minutes into the past and told me what the card was. See? So I already know what the card was. Now, the interesting thing was that if you had not been totally staring at the card, you would have noticed my future self in the back of the room, because when the future self left to go into the past, it takes up airspace. The air collapses back in. You would hear the popping noise. But what with the rustle and the crowd, everybody laughing, That's how magicians work. It's all misdirection. You up here, everybody's kind of laughing and enjoying themselves. You didn't hear the pop when the guy left. All right, so we got to find the card, right? So I got to pick out your card for you. Oh, this is too easy. Is that it? Oh, yeah, color was wrong. That one? That's it, okay. You see, that's why I'm not a good magician. I sort of blow the color. He sort of whispered it to me, but my hearing's not so good. So. Okay. So now we know so 4 dimensions, you take it for granted, but that's how magicians do tricks. Now you know their secret. It's just time travel. Okay, so now actually there's a way to make 4-dimensional spaces that's actually, again, it's sort of the cutting and pasting thing. And it turns out you can make any 4-dimensional space this way, which is you start with a 4-dimensional space. So a typical example is a 4-dimensional sphere. And here I'll write it out in coordinates. Think about so those of you who sort of who aren't quite familiar but with coordinates, think of it as you have 5 coordinates. We'll call them, these are numbers, x1, x2, x3, x4, and x5. And you require that their sum of their squares and they should sum up to 1. So x1 squared plus x2 squared plus x3 squared. This should equal 1. And that set of numbers, that defines the 4-dimensional sphere. And how you can make any other space from that is you cut out something interesting and then it has a boundary, and you find something with the same boundary and glue it back in. And you can just iterate that, and you can construct any 4-dimensional space by doing that. And the problem is, of course, is that you can get the same shape by cutting it up in lots of different ways. And so that's not going to give us a good list because there are basically infinitely many ways to get the same space by cutting. But anyway, any given 4-dimensional space can be obtained by some sorts of cuts, but unfortunately infinitely many. So, so the question is, how can you tell when 2 4-dimensional spaces are the same? So what there's some sorts of classical invariants that have been known since, in some sense, since the early 1900s, which if the classical invariants are different, so these are basically invariants being numbers associated to a space. If they're different, then spaces are different. So these 2 classical numbers, one of them is called the fundamental group, which is not really a number, but it's something more subtle, which is called a group. But anyway, it's sort of an algebraic object, fundamental group. And the other is another algebraic object, which is called the homology groups. And those are the classical invariants. And the problem is until 1983, Simon's great breakthrough, if you had 2 spaces with the same fundamental group invariants and the same homology, you didn't know whether they were different or the same. And so let me give you an example of what this means. So the idea is that what Simon discovered was that he used these new equations that physicists had invented to describe the 4 fundamental forces, and he figured out a way to count the solutions to these equations. And if you had 2 spaces with the numbers, the counts were different, then the spaces were different. If the counts were the same, you weren't sure whether they were different or not. But if the counts were different, you knew the spaces couldn't be the same. And so let me give you an analog to think about. So suppose you go home tonight. You're thinking about my lecture. You fall asleep, but you have your window open because nice cool breeze blowing in, and then there's a strange pulsating blue light, woo, and some noise, and an alien spaceship sort of settles down right outside your window. Woo, and the door opens, the alien comes back, you get tractor beam, takes you out of your bed, brings you into the spaceship, and you fly someplace and you're let out and you're in a city. It's in the morning, you're in a city. You say, how do you know if you think it was a dream? Get out of bed, open the door, and it's a strange city. So, or maybe it's not a strange, you're not sure. You can't hear what people are saying, you don't know about language. How do you know is it the same planet? Did the alien take it to their planet, or is it the Earth? So you're not sure. So you look up in the sky, there's one yellow sun, well, that's good. But maybe there's a yellow sun and then there's a little red sun next to it. Well, there's two suns instead of one, you know it's not the Earth. So that's sort of an example of a counting invariant, right? And you know, if you see two suns in the sky, you know, that wasn't a dream. The alien really went and got you. And so this is sort of the analog of, I mean, not I'm being a little facetious, this is not quite the analog, but the idea being that Simon took the four equations, and so what are these equations, and what are these forces? So there are four forces. One is called electromagnetism. This is, of course, electricity and magnetism. We know since Maxwell that they're related. There are two, basically what you're given is you're given two vectors in space that depend on time, t, and a coordinate x. And you're given, that's the electric field, it's a vector, it has three components in the three directions, E3, E2, E3. They're both functions of time and space. They depend on time and space. And Maxwell, and then there's a B field, which is the magnetic field, BT, and the version of, there's Maxwell's equations, and the version of the equations that I worked on, you know, and that Professor Donaldson exploited was a version of the equations that said E plus B is equal to 0. So those are called the sort of self or anti-self dual equations for electromagnetism. So that's the first force. The second force is one that the next two forces are subatomic forces, and the next one's called the weak force. And the weak force is, I don't know if in the old days, I don't know if they still do, but they used to have watches with a radium dial that glows in the dark. You could see that because a little green glow is radium is radioactive, and the green glow is caused by radioactive decay. And the sort of radioactive decay in a radium watt, I don't know if you young people know about these things? Maybe you guys all have, you don't even have watches, right? You all have cell phones, so you don't need a watch. But the weak force, anyway, radium, the decay, radioactive decay is caused by the weak force. And the weak force is described, it was a tremendous breakthrough in physics where Weinberg and Salam, Stephen Weinberg and Abdus Salam proposed some equations which are more like the ones that I worked on at Professor Donaldson, which involve essentially three electric fields and three magnetic fields. So you can think of it as a 2x2 matrix. You'd have E1, and here we'd have E2. Well, let's call this one E3, and here I have E1 plus I E2 minus E1. And here I have E1 minus I E2, and plus. And here I'd have put an I. I is the square root of minus 1, so there are imaginary numbers involved in this game. E3, so that's an E vector, an E matrix, call it E, and then there's a corresponding B matrix. And the equations, and I understand Professor Donald will say more about this in his lecture, but the equations that were used were the weak force analog of the self. These are the anti-self dual Yang-Mills equations. So Yang and Mills first sort of talked about these kinds of electric and magnetic fields. Just for completeness, the third of the forces is called the strong force. The strong force is the force that is responsible for the nuclear energy that powers the sun, that nuclear bombs, things like that. And then there's gravity, The strong force is given by a similar sort of pair of matrices, E and a B, but now there are 8 components instead of 3 components. It's again a Yang-Mills field. Then there's gravity. Gravity is very different, and actually gravity is Einstein's equations, and a variant of the gravitational equations were used by Perelman using work of Richard Hamilton to do the 3-dimensional problem. But gravity doesn't seem to, Einstein's equations don't play a big role in 4 dimensions, but you know, they might. I mean, at this point, they don't seem to have, nobody knows how to plug them in. Okay, now what happened was in 1994, Ed Witten and Nat Seiberg proposed a new set of equations. Well, they were studying them for reasons of physics, but Witten suggested these might be useful to study 4 dimensions. And so I and my friends and colleagues took him up on that, and to our great surprise, well, we shouldn't have been surprised because he's quite a brilliant man, but he turned out to be right. I mean, they were, so these are called the Seiberg-Witten equations. So I think I'm spelling his name wrong. It's EI. And the Seiberg-Witten equations, in almost all cases, they carry the same information as the equations that Donaldson used. And by counting solutions of these equations instead of counting solutions of the self-dual equations, you get invariants of manifolds. Apparently, these counts carry the same information, but it turned out Seiberg-Witten equation counting was much, much, much easier to do. People worked extremely hard to be able to actually get, you know, you give an example, can you compute the invariance? And with the original Yang-Mills equations, it was extremely difficult to do. And we, you know, half-jokingly said we need to have a new journal called the Journal of Papers that are more than 200 pages long. But now the Seiberg-Witten equations were much easier to use because they're in a lot of ways simpler. And so there's an electromagnetism in E and a B, E plus B, and then there's, so Dirac invented the idea of a spinor being a 2-component complex field, complex function of each position. So there's an extra field, which is a spinor, so there's an alpha and a beta. So alpha is a complex number, it has a real part, and square root of -1 times its imaginary part. And beta is also, so it's 2 complex numbers which depend on, again, 4 coordinates. And so there's sort of a quadratic term here, which I won't write down, but it's a quadratic in the spinor. And then there's an equation for the spinor, which is just Dirac's equation that he used to describe electrons. And so the Seiberg-Witten equations, counting these invariants, this was a great advance. And so you count solutions in a rather creative way, and you end up with an invariant. And so, so that was sort of the next part of the story. And I started playing with these things, and I realized that if you do it, you can perturb these equations, and the idea being the count actually doesn't, you can make the count even if you change the equations a little bit, it'll still give you the same count. And so what I did was I said, well, okay, so let's think about perturbing these equations. We'll put a parameter r, which is a positive real number, we'll put it in front of the q, and then let's take another object, which I called omega, I times omega, imaginary number. And what happens is if you take r very large, and I sort of asked myself, well, what happens if you take r very large? And if the omega has certain nice properties, and the nice properties are characterized by, it's called what's called a symplectic form. And so this only works in certain cases. You can do this. But what happens if you take r very large, you see the spinor has an alpha and a beta. And what happens is the beta part goes to 0. The beta part tends to go to 0, gets really small. And the alpha part wants to have norm 1. But it can't everywhere. And what happens is, what's interesting is the places where it vanishes, where it doesn't have norm 1. And what happens in 4 dimensions is that the alpha part vanishes along a nice surface in your four-dimensional space. So what happens is that the alpha part finds these really beautiful surfaces in the four-dimensional space. And these surfaces happen to have been surfaces which were investigated and sort of discovered or first investigated about 5 years earlier by a Russian mathematician, Mikhail Gromov. And they're called pseudo-holomorphic curves. Pseudo-holomorphic. And they're the analog of holomorphic. Well, they're the analog of what complex surfaces in C2. So if you think about, again, two complex numbers, two complex variables. So think of C2 as having complex coordinate z, which is x plus iy, and say w, which is u plus iv. And think about the zero locus, say, of some kind of object like this, w squared plus z plus 1, something like that. The zero locus of that is an example of what people call holomorphic, and Gromov called these things pseudo-holomorphic. And they're very rigid, and so when you find them, they're telling you something about the four-dimensional space, and essentially the counts of solutions that Seiberg-Witten equations are counting and the self-dual equations are counting, they're really counting numbers of these very rigid surfaces. So we get a very geometric picture of what's going on in that if you get some large count, it means that your space can have lots of these very rigid surfaces, and if the small count of space is too simple to have many of these rigid surfaces. So the whole idea being that now we kind of understand to some extent the geometry of what these counts are telling us, or telling us about these rigid surfaces. I mean, at least that's a hint of what they're telling us. We still don't really know how the rigid surfaces control the space, but. And now what happened, sort of a much more recent advance is that there's a way to use these Seiberg-Witten equations to study dynamics and in 3 dimensions. And so what I mean by dynamics, one has a sort of vector function. So let me give you the example in you have a vector function of space of 3 coordinates. It has 3 coordinates, v1, v2, v3. And you want to ask, well, let's look at the trajectory of a particle which is being pushed by, think of it as a force. So dx dt is v of x of t. And you want to ask for solutions of this equation that are closed. So typically, the typical trajectory won't be closed. It just gets pushed along by v. And of interest is the case where, counting closed trajectories. And so this is a question in dynamics, because you can phrase like the dynamics of a particle moving under a force in terms of, trajectories under of a sort like this. And so there are very interesting question in dynamics is when do there exist closed trajectories? And it turns out that, that there's a special kind of a dynamical system which is called a a Reeb vector field, which I will give an example of in a minute. There's called a Reeb vector field, and Alan Weinstein postulated about 30 years ago that in this context of Reeb vector fields, there was always at least one closed orbit. And this is something I proved again using the Seiberg-Witten equation. It's the same idea, really. I looked at the 3-dimensional version. The 3-dimensional version is you just write down the 4-dimensional and assume everything's independent of time. And you take R very large. In this case, the beta thing again goes to 0, and the alpha thing wants to be 1, but it has to be 0 in some places, and those are the closed trajectories. And I used work of my colleagues Tom Rofke and Peter Kronheimer, and they gave me some topological information that said there always had to be solutions with this property that the alpha spinner had to vanish somewhere. So the idea being that what you ended up with is a proof of this Weinstein conjecture coming out of the blue from someplace totally new, which is you just take R very large and you see right away that very easily that the zero locus of the alpha spinner has to be a closed orbit of the Reed vector field. So I'll end, I'm just about out of time, so I'm going to end with two things. One is give you an example. What do I mean by, what are these Reed vector fields? So the analog is this. I'm looking for trajectory. So a trajectory being t goes to x1 of t, x2 of t, x3 of t. So you think of just a moving particle in space. And so that's x of t. And the vector field equation, and this arises very naturally in dynamics, but I don't really have time to explain why, but it's of this sort. It's the curl of something else, which I'll call A. So your usual curl from your multivariable calculus class. But the constraint is that the dot product of A dot curl A has to be this dot product. This has to be always positive. It can't be zero anywhere, or always negative, but it can't be zero. And if you have an A of this sort, then it turns out that there's always a closed trajectory of this thing. So you get a kind of an existence theorem of closed trajectories. Okay, so I'm going to end by telling all you youngsters where we stand in the field here. Okay, so just to let you know that there's, we're nowhere near understanding things. So it isn't as if this is the end of the story. So, so there's lots of work for young people. So where do we stand? So the question is, are all spaces, we have the classical invariants, we have Seiberg-Witten / Yang-Mills, invariants Professor Donaldson discovered. We know that if two spaces have different invariants, they're different. What we don't know is if they have the same invariants, must they be the same? Some cases you can tell. I mean, if you count, some cases you can just stare at them and tell. But the only way to tell now, the only techniques we have now are just trial and error. Some people, you just stare at it long enough, you can say, well, yeah, it's just the same space. I just happen to be looking at it from, Munich, Germany instead of Hong Kong, but it's really the same Earth. But in other cases, wouldn't know. So the question is how to tell when two spaces are the same. That's really a fundamental thing we don't know how to do now. So you can classify people's personalities on how they tend to lean in this question. So there's the optimist, or I don't know, optimist might be the wrong word, but the optimist would say, well, yes, it's just classical invariants and these new invariants, and if two spaces have the same, then invariants, they're the same. So that's the optimist. Then there's the kind of a realist who might say, well, there's probably some more invariants you have to discover, but basically you're on the right track. And then there's this truly pessimistic, very kind of clinically depressed person who would say, 4 dimensions is way more complicated than you ever can imagine. Okay, so now my personal philosophy is as follows. First of all, I tend to be a true pessimist because I've concluded that if you're a pessimist, you're never disappointed, and every once in a while you're pleasantly surprised. Whereas if you're an optimist, you're continually disappointed. Of course, you probably don't care because you're an optimist. But the other thing is, being a pessimist, I vote for the pessimistic point of view because it's the patriotic point of view. In other words, the worst possible thing would be for someone to prove a theorem now that said, at least for me, the classical invariants and the Seiberg-Witten-Donaldson invariants are all there is, because that would put me out of work. I would then have to actually make a living like a normal person. So I think it's probably better for the world economy, given the bad news we hear all these days about the economy, for someone to actually prove the sort of more pessimistic thing, because that would keep people employed longer. And so I will end on that pessimistic note, and I thank you.
I hope Professor Taubes would be willing to take a couple questions. Anyone?
You all understand perfectly. It's good. And that never happens usually. But.
Briefly, is it possible to tell us what you mean by two spaces being the same or different?
Well, yeah. I mean, that's, of course, a subtle point. But there's a notion, I'm going to have to get technical here because one has to, of course, define the terms. But there's a notion of a homeomorphism, which is a one-to-one continuous map with a continuous inverse. And actually, Michael Friedman classified these, topological spaces. Now, what we're interested in spaces that have a property of being differentiable. So that means you can do calculus on them. And so what you need to say two spaces are the same is you need a one-to-one, infinitely differentiable. Actually, it turns out it just needs to be able to do one derivative, and then you can do them all. But anyway, infinitely differentiable map with infinitely differentiable inverse. So that's the equivalence relation, diffeomorphism. And that's the technically. So, for doing physics or anything else, you need to be able to take derivatives. And so what's interesting really are spaces where, you can take derivatives. So we have to talk about diffeomorphisms. And that's in some sense why these are differential equations that are giving new invariants, because if they didn't take derivatives, then it would be, I suppose one could invent invariants that saw differentiable distinctions that didn't take derivatives, but it seems would be harder to do.
Yep. So we go.
Does your pessimism extend to physics as well as mathematics on this question? And I mean the link between the kind of physics that you're referring to and the kind of geometries involved. Do you think that where's that going to go?
Yeah. So I would be. Let's put it this way. I don't want to get into religion or anything like that, but if I was a religious person, I would be profoundly disappointed if the universe turned out to be something we could understand. If there was I would prefer to be turtles all the way down, so to speak, and that it just gets more and more interesting. And if the answer was, well, it's SU3 plus gravity. Mm-hmm. I mean that.
It's too easy.
Then what would we do? Then we'd know the answer, and we'd have to learn biology now. I would prefer it to be interesting all the way down. That's my preference. Now, whether that's what I think will happen, I don't know.
Yeah, a question in the back there.
First of all, thank you for the lecture. I'm a physics major student from CHK. I got two questions. The first one is that can you give us some simple geometrical example for 4D cases? Because when we understand 2D, we can understand about the surface of the Earth, and then you talk about how to cut out them. But when you go on to fourth dimension, you skip that and go to 5 dimension. So can you please give us some simple geometrical example for 4D?
Of four-dimensional spaces? So you want two different four-dimensional spaces? Is that what you're?
Sorry.
I'm sorry. I'm not quite sure what you want me to do. So you want me to exhibit?
Can you give us some daily example that we can experience 4D?
Oh, two different four-dimensional spaces?
Yeah, sort of.
Yeah. Okay. So I mean, that's not.
I got the second question also.
Well, let me answer the first one.
Oh, yes. Thank you.
I can't keep two questions in my head at the same time.
Yes, thank you. Sorry.
Okay, so one example I already gave you was a four-dimensional sphere, right? So you look at five numbers, but you require their square, the sum of their squares to be equal to 1.
Oh, so it eliminates one of the 5.
What?
Oh, I see.
So that's a four-dimensional sphere.
Yes,
because
yes.
you
have talked
think
about it.
there you need 5 numbers, but you've constrained them so that their sum is 1. So actually you can solve one of them for the other 4. Another example, so this is called the phi sphere. Another example would be something we call S2 cross S2. Sorry? 4, yeah, sorry, 4, thank you. And another example would be, for example, S2 cross S2, where I give you 6 numbers, where you get 6 numbers, but, so that's the usual 2-dimensional sphere in 3-dimensional space, and then you have another set of numbers, so you have 2 different, so you have to give a point on both spheres. So you think of there are 2 spheres, and you can have any position on both spheres. So that's topologic. That has a different, actually, classical invariant than this one. Their homology is different. And so this one's called S2 cross S2, and this one's S4. Okay.
Thank you. And the second question is that as a physics student, I try to relate the 4 vectors. So in general relativity, we talk about 4 vectors. 3 of them is about space, and 1 of them is about time.
Right.
And you also talk about the 4th dimension is about space-time.
Yeah.
So it's certainly about time, but in space, can I just heuristically think that the 4th dimension is about depth? What do you think about? Even the Bible tells us that God's love is about length, breadth, height, and depth.
Well, I mean,
So
the
it's
thing,
because
yeah.
you also talk about how deep is the inner boundary of the space.
Yeah, well, I don't know if I'll answer your question quite satisfactorily, but the point is, on a large scale, things get curved around. I mean, that sort of, Einstein's equations, and you get regions of very high curvature, and so what happens is that, of course, there's a difference in that the kinds of spaces that arise in general relativity are very special. They have the property that you can distinguish, the time-like direction from the space-like direction. Now, that's a question which involves these classical invariants. You need to have a certain, property of the space to be able to do that. But there are other spaces. So a space that you couldn't distinguish globally, time and space, is not one that could, in principle, arise, in general relativity, but at least in the simplest versions. Although people who do quantum gravity talk about all kinds of spaces, not just these special ones where there's a specific time-like and space-like directions. So I don't know if that answers your question or not. But yeah, okay.
Yeah, you say a last question? Yeah. Oh, yes, I've read you. Yeah.
Okay, I'm an engineer, so I think in the classical sense, in classical electromagnetics, E and B always point in different directions. How could E plus B equal to 0? Can you explain that in simple terms so that we can understand?
Well, I mean, locally you could have E plus B. I mean, they would, but we're thinking about I mean, if you think of E as just the gradient, then if the gradient, let's see. So I'm going to try to answer your question without making a fool of myself. I have to think about your question before I answer it. So maybe we'll talk afterwards. But you can have that locally. I mean, one thinks of E and B, the E fields is extending out of a charge, and the B fields, not having a source. But if you imagine a space which is slightly more complicated than R3, so for example, the space I drew S2 cross S1, where you have the inner sphere ball you've taken out, then you can imagine, the E directions, but you can have the E field sort of curving around. So the vacuum Einstein equation, I mean the vacuum electromagnetic equation, dE dt is, what is it, curl B, and dB dt equals minus curl E. So, I mean, the reason, if I think about these, locally you could have E and B pointing the same direction, but, globally on R3, there are constraints. But on a general, more complicated large-scale structures, if the space were more complicated at large scales, then you could have that happen. I mean, that's a loose answer. I'd have to think about it to give you a real precise answer.
Okay, thank you very much. In order to allow enough time for the second lecture, let's stop the questions right here. Thank you very much, Professor.
Thank you, Professor Taubes and Professor Kwok. So now we will have an intermission of 10 minutes. So tea and coffee will be available at the foyer. So please enjoy yourselves at the foyer, and please come back by 11:55.
Very clear.
Thank you.
What? Oh, thanks. Well, I hope I gave the background for you to take on. Whenever I do that card trick in public, I always blow it.